Okay, hi, welcome to the online office hour for statistical inference and um, mathematical biostatistics boot camp 2. Um, I realize I may have not have sent the email out to the statistical inference crowd, but so at the bare minimum, this will be for the boot camp 2. Um, let's see, but I will, for the inference class, also answer some questions from the forums. While I'm waiting for some viewers to come on, why don't I answer some of the questions from the forums? Okay. So one question that comes up a lot is, Professor Caffo and the TAs, is there a specific reference textbook or online material that you would suggest? And one of the community TAs gave a bunch of nice references, including Open Intro, so I would say the book by Rice, Mathematical Statistics, with, well, let me see the exact title. Is it Rice, Mathematical Statistics and Data Analysis? I think that's a great book. Let me, I'll add this in the forum. But that is a very good reference book, and in fact, I'm just going to put down here to also see this discussion, so that the folks on the board. So that book is very good. There's a book by Rosner, who's a statistician at Harvard, that is very well known in biostatistics. It's somewhat encyclopedic, but it is extremely thorough, and it covers nearly everything in the field of biostatistics that you could think of at a level that's a little bit mathematically below the Rice textbook, but it covers way more information. So that book's it's very good. Another textbook that I like, the Open Intro textbook, was mentioned on the forums. That's a great book. So there's a book on Bayesian biostatistics. That's a nice book. Who's the author of that? The Bayesian biostatistics. So that's Lasafra and Lawson, two very good statisticians. So that's a very nice. That I've seen that book. It's quite nice. But was that the one I was thinking of? I guess it's the next edition. I think Lawson was the only author when I saw it first. But anyway, they're both very good statisticians. That's a nice Bayesian book on biostatistics, if you'd like. And then there's a book by Hegarty. Let's see. Yeah. So there's a book, Van Bell, Fisher, Hegarty, and Lumley. So that's a star-studded cast there that wrote a book called Biostatistics and Methodology for the Health Sciences. It's really nice. I would look at that one as well. But anyway, I hope that answers that question in terms of the books, the references. I think for the class you can probably get by without a book, and I'm hoping at one point to write a kind of Kindle-style book for this class so that people can get it for a couple $. Let's see. We'll go back to the discussion forums and see what other. Let's see what other questions. Relationship. Oh, so someone has, what's the relationship to our in-person classes? So at Johns Hopkins. So this class is, if you take Mathematical Biostatistics Boot Camp 1 and 2, this is very similar to the first and second term, which is then one full semester, a little bit longer than a semester, of our introductory biostatistics master's method sequence. So it is not a replacement for our theory sequence, which has covers the theory in a lot greater depth. So this is like one semester of our year-long core method sequence. If you wanted to round out this class with everything that our master students get for methods, it would be this sequence, plus then another sequence that covers regression models and GLMs. And we actually have a Coursera course on regression models now. I teach it, and it's in the data science specialization, and it'll be coming out next month. So you can take a course on regression models and GLMs. That course is dramatically reduced relative to what we teach our SCM students. These sets of courses, Boot Camp 1 and 2, are pretty much identical to what our master's students would get in the first semester. I think that answers that question. So if you can do this class and it's easy for you, then you're roughly, I think, well calibrated to what an SCM Master's Biostat student should know for methods. Now you probably, I think students often find the theory class a little bit harder. So take that for whatever it's worth if you're calibrating yourself relative to what you would think a master's degree in biostat would give you. But in terms of the methods part, if this class is good for you and you feel like you understand it well, then you have a good equivalent understanding to what a student in our methods sequence would have. It'd be nice. We should get a theory sequence on here too as well. Okay, so let me see the discussion here. All right. Let's see. Okay, back to the professor's forum. Is it possible? Let's see. So someone asked, is it possible to have all the material from the beginning? So this is relevant for the boot camp class, but not so much so for the inference class that's also going on right now that I'm teaching on Coursera. So for the boot camp class, all of the lecture materials are on YouTube. So there's the discussion there, and let me get the YouTube link. So this link will be posted in the relevant discussion forum. So let's see. You can, if you look at my YouTube channel, you can see not only you can see my cat videos and that sort of thing, but also I have a some playlists that show the whole collection of lectures. And then so all the lectures are on YouTube, and then okay. Let's see. What's next? What was the other question? Is it possible? Okay, so that covers everything from the professor's forum in boot camp. Yeah, so we have something called the staff forum in. Oh, looks like the community TAs have answered those questions, but let's see. Okay, so let's look at some of the questions that were posted to the QA. Okay, so so someone writes, Rui Zhang writes, Dear Professor, which is a very nice salutation, thank you. But you could just call me Brian if you want. Regarding the question 9 of quiz 1, I used the power formula. Okay, so all right, so the basic question is, can you, if I'm summarizing this question correctly, it's basically, can you give me a hint about question 9 of quiz 1. So let me pull it up, and I'll see what I can do. Quiz 1. Sorry, it takes me a minute to navigate the website. Quiz 4, quiz 3, quiz 2, quiz 1. There we go. It's going to yell at me. All right. Question 9. Question 9. Okay, so this quiz question says the Daily Planet ran a story about kryptonite poisoning in the water supply after a recent event in Metropolis. Their usual field reporter, Clark Kent. You might notice I got this question from somewhere, from a setting. Called in sick, and so Lois Lane reported the stories. Researchers planned to sample 280 individuals from Metropolis and a control city, from Metropolis and a control city. A control city. Oh, and control city Gotham, and we'll compare mean blood kryptonite levels between the two cities. They expect to find a mean difference around 2. Assuming a two-sided z-test of the relevant hypothesis of 5%, what would be the power? Assume that the standard deviation is 12 for both groups. Okay. And let's see. Let's see what Rui wrote on his question over here. Let's see. Let's see. Probably, yep. Okay, so. One over 2. Okay. Equals 1. Let's see, I'm trying to find where the error is in what they wrote. It looks good so far. 0, 0. Okay, let's. I'm having trouble spotting the error in your code. Why don't I just kind of work through my thinking on the problem, which is maybe a little bit easier to do, and that way I think, and I'm quite confident that the answer in the quiz is right. So let's see, file, new. Back. I'm going to share the screen here. Let me get, let's see, file, new document, landscape. Okay, there we go. And then let me get this over here. Okay, and I want to screen share, and I want to share that screen. Okay, there we go. Okay. So So, and then let me bring up the quiz question here. So we have H naught. Let's see if this, just double check and make sure that's showing up. Yep, it appears good. So here we have H naught mu metropolis equal to mu Gotham versus HA that they're not equal to. And our test statistic is going to be X bar for metropolis minus X bar for Gotham divided by the standard error for the difference in the means. Okay, which this standard error works out to be sigma times 1 over n for metropolis plus 1 over n for Gotham. Okay, and we're going to reject if our test statistic is bigger than 1.96. Well, absolute value of the test statistic is bigger than 1.96, right? And so then the power is the probability that we reject given HA, okay? And the way we've specified HA in specific here is that the metropolis minus mu Gotham was 2. Okay? So here we want the probability that the absolute value of the test statistic is bigger than 1.96, given that the difference in the means mu metropolis minus mu Gotham is 2. Okay, so that's the probability that X bar for the metropolis minus X bar for Gotham over sigma over 1 over, it said 288, 1 over 288, okay, greater than 1.96. Okay, I'm sorry. Given that mu metropolis minus mu Gotham was equal to 2. Okay. Well, absolute value of this guy. Okay. So this test statistic right here, that test statistic, it's actually kind of, and this works out to be, sigma is 12. Oh, and I need my 1/2. I need my 1/2 there. Let's see. This guy times sigma works out to be 1, and we know that X bar metropolis minus X bar Gotham. Let's only consider the positive probability. Let's ignore the negative probability. So the probability that this is, so this part turns out to be 1. And let's look at the probability that that's bigger than 1.96 without the absolute value, assuming that the probability that it's less than negative 1.96 is small enough, given that the true mean difference is 2. Let's assume that that opposite probability is small enough to not worry about. Okay, this, so we could subtract 2 from both sides, which is exactly what the person is suggesting, and that works out to be the probability that this guy, which is now a z statistic, is bigger than 0.04. But if you look at the normal distribution, here's 0 and minus 0.04. If you look at that's basically there. So that's got to be about 50%. So now I think I understand where this person's error was. So that's gonna be about 50%. I think their mistake, just reading over the statement, is that We add a page. How do I add a page? Insert page. Okay. The probability that the absolute value of the test statistic is bigger than 1.96 is equal to the probability the test statistic is larger than 1.96 plus the probability the test statistic is less than negative 1.96. And I think what the mistake they're doing is they're calculating this and assuming that this number is equal to that, but it's not, right? That when you subtract off 2 in this case, you get the probability that a test statistic is less than negative 3.96, which is, this probability is effectively 0. So I think they're counting this probability twice instead of and mistakenly assuming that that probability is roughly equal to that probability, when in fact this probability is very small. The intuition behind that is, if the difference in the means, if the true difference in the means really is large, right, it's 2, so the difference under the alternative. So if the difference in the means is truly large, then the probability that you correctly reject accidentally with the test statistic very extreme in the wrong direction, suggesting that the mean for Gotham is much higher than the mean for the metropolis, the probability of that occurrence is very small. It's 4 standard deviations away. And I think that's the mistake in that's the mistake in the logic there. Let's see. I think that's a pretty thorough answer to that question. But let me just double check and see if I can actually understand. Yeah, that's definitely the error that's in this. That's definitely the error that's in this that statement there on the website. Okay, good. Let me see if I can bring it out of screen share. There we go. Okay. Let me get back to the forums. Okay. Let's see. Let's see. There's some questions in the forum on. Let's see. So there's a couple questions on the forum on the numerical input for the inference class. Okay. So I will handle that for the inference class questions. I will handle it. It looks like the main questions for the inference class all relate to numerical formats for the forums. So I will answer those directly, because that I think that requires a typed out response. So I will answer that directly on the forums themselves. Let's see. Formats, citations for office hours. Incorrect video posted. Oh. Okay, so it looks like most of the questions being asked on the inference class are kind of foibles, and I will correct them. I will correct them right now. But it doesn't seem that there doesn't appear to be a lot of um, input type or technical technical statistical questions. It looks like most of the questions are actually um, uh, class format questions, and it looks like there's a couple things I need to handle. So I will do those. And so just to remind everyone that the QA is possible. Okay, so let me start answering some questions from the QA. Let's see. Okay, and it looks like, let's see, all the QA questions have one. So here's one that says, can you give an example, can you give the most trivial example of a 95% interval that has coverage less than 95%? The most trivial example of that is if you create a confidence interval for a binomial proportion using the formula p hat plus or minus z 1 minus alpha over 2 square root p hat 1 minus p hat over n. So that formula is based on the asymptotic distribution of p hat, right? P hat minus p over its standard error has an asymptotic standard normal distribution. Because of that, when you calibrate it with that 1.96, right, that is supposedly to give you a 95% confidence interval, that is based on an infinite sample size, right? The limit as that distribution, as the n goes to infinity. But you actually have a finite sample size. So if you were to simulate binomial data, calculate the confidence interval that way, and do it over and over and over again, and get the exact coverage of the interval by doing that simulation over, and in fact you don't have to do this with simulation, you could just do it with the binomial formula. But let's just say, to make it conceptually simple, that you did this by simulation. The percentage of intervals that would contain the true value of p would be less than 95%, because the central limit theorem is only an approximation. So the calibration that you use, the alpha that you plugged into the normal distribution to get the quantile to get 1.96, because that is based on a distribution that isn't the actual distribution of p hat, the coverage of that interval is in fact not 95%. It's less, and can be quite a bit less. Okay. And this, let's see, this is the question I answered from Rui, but I apologize, I didn't actually select it. So as far as I can tell, the mistake here is the counting this probability, the 0.04, counting it twice, when in fact the other side is not of equal probability. Let's see. Okay, let's see. A question was asked regarding medians in Quiz 1, question 7, that I'm hoping you can see in the forum. Let's see if I can get the forum link here. Quiz 1, question 7. Quiz 1, question 7 is about the mean, not the median. You asked a question regarding, let me see if I can find what you mean, what you're implying here. Error in Quiz 1 question. I think the answer is wrong because of the following. Suppose you have two standard uniform rows. Question 7. Let me read what this question. I'm not seeing how this question relates. Consider, so quiz one, question 7. Oh, I see my mistake here. I'm looking at the wrong class. Okay. Let me see. Quiz 1. I think I'm teaching too many Coursera classes simultaneously right now is the problem. Okay, quiz 1. Section manager. All right, quiz 1. All right, question 7. Okay. If a density is symmetric about 0, can we say that its associated median is 0? Okay. And yes, so I am going to approve the community TA's answer to this. So let me share my screen again to answer this question. File, pages, pen page, okay. And then I want to do screen share. Okay, so let's just talk about distributions in general. If you have a distribution like this, here would be the mean, the median, and the mode. If you have a distribution like this, right? The mean, the median might be here, but the mean would probably be pulled a little bit to the right of it, and the mode would be right there. Okay, right? So let's look at another distribution. Imagine you have a distribution like this, where let me do a better job of it. Distribution like this. If you have a distribution like this, you have the mean and the median, but you have two modes. You have that mode and that mode. Okay, so that's a bimodal distribution because it has two modes. So if your density, so what are we saying? We're saying if your density is symmetric about 0, then what we're saying is no matter what you draw on this side, the opposite side looks the same, no matter what you draw. Okay, and then you can argue if you have to if you flip the density around and it's the same, then it must be the case that 50% of the probability lies up here and 50% of the probability lies down there. So that 0.0 must be the median. I think the confusion in which the community TA appears to have acknowledged is that if you have a bimodal distribution, right, this still is the median, right? 50% of the distribution lies below it, and 50% of the distribution lies above it. But the mode is different, right? There's two modes, okay? So I think the community TA is right in that the question is confusing the median and the mode. Okay. Okay, so done with that one. And select and done with that one. Okay. let's see. Hi, Brian. Sorry I won't be able to join in on Wednesday, but I'd still like to ask the question. So can I look it up on YouTube? Monte Carlo methods just came out of nowhere for the two-sample test. Can you explain more on how it works and when we can use it? Oh, okay. So Monte Carlo is the process. Monte Carlo is the process of using simulation to figure out something about a statistical procedure. So if you wanted, for example, to if you wanted to see, we talked earlier about the binomial coverage probability of a confidence interval. So if you wanted to see whether or not a confidence interval procedure that's supposed to have 95% coverage, if it actually has 95% coverage, what you would have to do is you would have to simulate the confidence interval procedure, or what you could do. I shouldn't say what you would have to do. There's two ways. One is figure out the math, and the other way is to simulate the confidence interval procedure and do it over and over and over again. And the percentage of times that your interval covers what it's trying to estimate, that would represent the coverage probability of the procedure. So, for example, if you take a binomial confidence interval procedure, p hat plus or minus the two standard errors, you might ask yourself, well, what coverage does that actually have? It should be something near 95%. It turns out that it's not 95%. So imagine if you had a true success probability of the coin of 75%, so it's a funny shaped coin that gives heads a little bit more often than it gives tails, right? If you were to generate data, calculate the confidence interval, see if it covers 0.75, and then do that over and over and over again, that would give you the confidence coverage probability for that particular procedure in the specific case when p is 0.75. And then you could repeat that over and over for different values of p, 0.74, 0.73, and so on, and you could see how well it works. Anyway, the principle of Monte Carlo is this idea of using the computer to perform that experiment. And yes, you can't do the experiment infinitely many times, but you can do it enough times because it's running on a computer. You can do it enough times that you can just assume you've run it infinitely many times and evaluate these statistical procedures via the so-called Monte Carlo process. So anyway, all Monte Carlo is the idea of doing on the computer the frequentist experiment of repeating IID repetitions of the experiment over and over and over again in order to evaluate a statistical procedure, whether it's an estimator or a confidence interval or whatever. So that's all that Monte Carlo is. It's the idea of using simulation to evaluate statistical procedures. Question 5 of quiz 1. Let's see. So I don't know if this is quiz 1 from boot camp or quiz 1 from stat inference. So question 5 of quiz 1. Here's one way to test. Okay, so question 5 of quiz 1 from stat inference doesn't have any R code, so it must be question 5 from quiz 1 of bootcamp 2. Okay. So the question asked to give a 95% T confidence interval for the ratio of waiting times, where here the waiting times were logged, and how do you do that using a t confidence interval? So let me just see. Their waiting times in natural log of hours were okay. So the question gives waiting times in natural log of hours. So at any rate, imagine. So I don't. I say refer to the previous solution, and that actually has the same data. So the code that looks like the code that has a little arrow sign. Let me. The code that has a little arrow sign like this, new arrow sign, and then it has C and a bunch of numbers, and old arrow sign has C and a bunch of numbers. That's this arrow sign is assignment. It says assign to the variable new the vector of these numbers, assign to the variable old the vector of these numbers. And then t.test is the function for computing the t-test in R. And so if you do t.test new old, it does the t-test. And then remember, and then this function t.test assigns output to a R structure called a list. The way you can grab elements of a list is with the $sign operator. So the $sign operator grabs elements of the list. So $conf.int. So t.test evaluates the t-test. $sign takes the output from that function and then grabs the relevant list element. In this case, the list element is the confidence interval. And so this now whole thing returns a length 2 vector that represents the represents the confidence interval. So then if you exponentiate that, then that would exponentiate the two endpoints individually. Okay? So that's how the R code works. And then let's see. I see that you start talking about coverage of confidence intervals, but I didn't see a definition of it, or maybe I missed it. Can you define it? Yes. So the coverage of a confidence interval is the percent. If you were to well, let me think of a couple ways to define this. So the technical definition of the coverage of a confidence interval is if you were to construct that confidence interval over and over and over again on IID experiments, it would be the percentage of times that the confidence interval covered the value of the parameter that it's estimating. Okay? So the coverage is it's really what defines the confidence interval. It's the probability the interval, the random interval, contains the parameter that it's estimating. And the way to think about that is if you were to repeatedly perform experiments, 95%, if you construct 95% intervals, ideally 95% of the intervals that you obtain would contain the parameter that you're trying to estimate. Another way to think about the coverage, you could think of it in terms of error rates. So the error rate for the two-sided hypothesis test, let's say, of difference in two means or something like that, say you set a type 1 error rate of 5%, then the associated confidence interval that you got by inverting that hypothesis test would have coverage 95%. So if you find it easier to think in the terms of the hypothesis testing and error rates, hypothesis testing error rates, just you can calibrate the confidence interval coverage relative to the associated two-sided hypothesis test that you could invert to get the confidence interval. But the strict definition of confidence interval coverage is exactly that. It's the probability that the random interval contains the parameter that you're estimating. So if it's a binomial confidence interval, then it's the probability that p hat plus or minus 2 binomial standard errors covers the true value of p you're trying to estimate. And as we mentioned earlier on in the lecture, you chose that 2 that 2 to in order for in the hope that your confidence interval will have coverage 95%. However, that hope is given by the central limit theorem, and the central limit theorem is only an asymptotic approximation. It's not the actual binomial probabilities, and so the actual coverage of the interval that you constructed that way is different from the coverage that you want and that you assume by using the central limit theorem. So that's what that earlier discussion was about. Okay. Let's see. I don't see any other. Is there any other questions from the audience? I think probably what I'll do now is I'll go on stat inference and maybe address some of the questions that maybe don't work so well in the video format. There's a couple of technical errors that I just course delivery technical errors that I need to address there. So I'll do that. Let's see. Thanks everyone for listening in, and I apologize for missing the office hours on Friday, but I'll have another office hours this Friday at 11, and make sure to post your questions to the forum. Make sure to post your questions to the Q&A for the Google Hangout, and I'll try and get through as many of them as I can in an hour. But usually there's not so many of them that I can usually do almost all of them in the hour. Okay, and thanks a lot, everyone.